Transformers were built for language. They expect a sequence of tokens, one vector after another, like words in a sentence. But an image isn't a sequence. It's a grid of pixels. So how did the Vision Transformer teach a language architecture to C? The answer is a surprisingly simple first step called patch embedding. Today we're going to walk through exactly how it turns a picture into something a transformer can read. Now, let's follow one image through this step, moving from raw pixels to a clean sequence of tokens. Start with the raw image, just a grid of pixel values with height, width, and color channels. To a transformer, this is meaningless right now, because there's no sequence here, only a two-dimensional array it has no idea how to attend over. Language models expect words in a line, one after another, and an image simply doesn't arrive in that shape. Then we chop that image into a regular grid of small, non-overlapping squares. Each square might be 16 by 16 pixels, and every square becomes one patch. A big picture turns into a modest number of these little tiles, laid out in reading order. That count is what the transformer will treat as its sequence length. So the patch size you pick quietly decides how much work the model has to do. Here's the clever move. Flatten each patch into a long vector, then push it through a single linear layer. That projection maps every patch to a fixed-length embedding, which is exactly one token. Suddenly the image is a short sequence, one vector per patch. The transformer never sees pixels again, only these tidy little embeddings it already knows how to handle. Finally, because attention itself is order blind, we add a learned position embedding to each token. Now the model knows which patch sat top left and which sat bottom right, and a special classification token is usually prepended to gather the whole picture's meaning. So why was this such a shift? Compare it to how vision used to work. Convolutional networks slide small filters across the pixels, building up features layer by layer. That baked-in locality is a strong assumption about how images work, and for years, it was simply how machines saw the world. The network assumes that nearby pixels matter most, and it only ever looks through that narrow, sliding window. Patch embedding takes a different path. Carve the picture into tiles, turn each tile into a token, and hand the whole sequence to a plain transformer. The model learns how patches relate through attention rather than having locality wired in from the start. Underneath, three simple ideas carry this entire step. First, splitting. The image is divided into fixed-size patches on a regular grid, and that choice of patch size trades detail against how long the resulting sequence gets. Second, projecting. Every flattened patch runs through one shared linear layer into a token vector. In practice, this is implemented as a single strided convolution, which does the cutting and the projecting in one clean operation. It's an elegant trick, and it means the entire embedding step is really just one efficient layer. Third, positioning. Learned position embeddings are added, so the transformer knows where each patch belonged, restoring the spatial layout that flattening threw away. Without them, the model would see a bag of tiles with no sense of top, bottom, left, or right, and the picture would fall apart. All right, let's lock in the essentials of patch embedding. Patch embedding is the very first step of a vision transformer, the move that let a language architecture process images at all. Splitting the picture into equal patches and linearly projecting each one turns a grid of pixels into a short sequence of tokens. Adding learned position embeddings restores spatial order, and the whole split-in project is neatly done by one strided convolution. Master this one idea, and the rest of Vision Transformers clicks into place. For more AI concepts explained in plain language, come spend a little time at Standarity.com.